two units we have discussed about the fluid statics and fluid surface tension. Now coming to fluid motion. Earlier we discussed only when the fluid at rest. Now the properties concerned with fluid in motion. Again it has been classified into two chapters. One is called fluid or hydrodynamics and other one as viscosity. In this fluid dynamics we go details. Later the fourth unit we take viscosity separately. So the third unit in general is fluid dynamics. The properties of fluids in motion. Fluids in motion. We discuss about two types, streamline flow and turbulent flow. That particularly we call under heading as types of streamline flow and turbulent flow. The details will come later. Just streamline flow and for a non-viscous liquid, we discuss on properties of streamline flow, about the critical velocity, law of continuity and line of flow, lines of flow. Under streamline motion of liquid, the meaning of critical velocity and its importance for streamline flow. What is the law of continuity and helps to know the volume of liquid flowing across any section. And what is the concept of lines of flows or tube of flow. Then coming to the energy possessed by a liquid in motion. Kinetic energy, potential energy and pressure energy. Second concept and Bernoulli's theorem. Applications of Bernoulli's theorem. Then the rate of flow of liquid, velocity of flow of liquid, velocity of efflux, time taken to reach the horizontal range, time taken to, so this is the brief of the particular chapter fluid dynamics. We first read that whenever a fluid flows, we are classified into two categories. One is called streamline flow and turbulent flow. Under turbulent flow, we are not considered any concept because there is such a randomness in the motion of the liquid. Under streamline flow, what are the properties? What is meant by critical velocity and also law of continuity and its applications. And when the liquid is moving, what are the energies that process kinetic, potential and pressure energy. And law of conservation of energy, the Bernoulli's theorem is designed and its applications of Bernoulli's theorem. And rate of flow of liquid, in that velocity of flow of liquid, velocity of efflux, time taken to reach the ground from any orifice the liquid is rushing out, and horizontal range, at what distance away from the container the liquid reaches the ground, and time taken to empty the tank. If you have any hole at the base or the bottom, what is the time it may take to completely empty the tank containing liquid. This is smart unit, but more important factor of these two. Law of continuity, Bernoulli's theorem, velocity of efflux, time taken to empty the tank. On these concepts, the questions are appearing in the NEET examinations. We have to go detail one by one. To begin with, the streamline flow. So the very properties, lines of flow will not intersect means tube may be of any variation in its size, narrow or wider. You are seeing a liquid flowing particular line. Every molecule is running on the same line. They not go from line to line. There is some orderliness in the flow. If any molecule is found to be on one line, that continues to be in that without changing the lines. That's the meaning of not intersecting the lines. And it across any section of area A1, if you see the molecule is having certain speed or velocity, that is found to be same at any point on the line of flow. The speed of molecule reaching that point is always remains same, no changes at all. Again, the volume of liquid flowing out per second may be V1. Let us consider in the line of flow the another area of cross section may be V2, where its velocity may become V2. And volume that comes out to be V2. Volume of liquid flowing out per second across any section of the liquid remains the same under streamline motion. V1 equal to V2. It is not just volume. Volume of liquid flowing across a section per second, irrespective of its size, remains same. That is the most important relation you require. And it can be shown that A1 into V1 equal to A2 into V2 is a constant. This itself we defined it as a law of continuity. So if area increases, velocity decreases, or velocity increases, area decreases. But total amount of liquid crossing that section in a given time or per second remains same irrespective of the cross-sectional area. And another is velocity of flow is very much less than critical velocity. Critical velocity is a particular maximum velocity or a velocity what the liquid molecules have during the flow. Above that, they lose the line of flow. Whenever liquid flow with a low speed, there is no any kind of intermixing possible or change of path seems to be necessary. But when the velocity increases after certain value, the particles may not be on the line, they go interchanging. Intersection or interchanging of the lines of flow possible even by keeping some obstacle in the path of the line of flow. Even though a streamline flow can convert into a turbulent flow, when you keep in the path of line of flow or tube of flow some solid obstacle, what happens is the lines will be stiff and they start whirling around it and turbulent motion begins. Under two conditions, a streamline flow can be converted into a turbulent flow. Number one, velocity should not exceed certain minimum value that we call it as a critical velocity. If it crosses that velocity, that itself is enough to change the sections. Second, even velocity is low, some obstacle come in the path of streamline flow. That also make the lines of flow to intermix and turbulence starts. But all discussions what we take in this chapter, ideal fluid, no viscous force, and liquid under streamline flow only consider. This relation is valid for any liquid which is moving under streamline flow and for ideal fluid. So with this, let me go to the concept of Bernoulli's. When we take a liquid in a tube and it is made to flow through a tube, there may be a difference of height, pressure P1, P2, pressure difference I call P1 minus P2. liquid is flowing through this. So when we consider a liquid is moving, possesses three energies. One is called kinetic energy, which may be written as half mv square, as you have studied in mechanics. Half mv square gives you the kinetic energy of the liquid in motion. The second, potential energy, that you are taken as mgh. Compared to this, the other end is at a certain height away from the ground. There is a difference of potential energy. Third one we taken as a pressure energy, that PRE mp by rho, where m is the mass of the liquid flowing, p is the pressure difference between the two ends of the tube, and rho is the density of the liquid. It is quite naturally you are knowing in different chapters. For example, if you go to the electricity, charges will move. Current may be constituted only when there is a difference of potential. Potential difference is must to constitute the electric current, motion of the charges. Second, you studied in heat chapter. Temperature difference is must for the flow of heat. When the temperature difference becomes zero, heat of flow seems to be ceased. Temperature difference makes the flow of heat. Potential difference makes the flow of charges. Like pressure difference makes the flow of fluid. And that is accounted energy that processed by the pressure difference, we call it as a pressure energy, mp by rho. However, three types of energy a liquid in motion possess: kinetic, potential and pressure energy. Here the concept of Bernoulli's theorem arises. For any ideal fluid, streamline flow, ideal fluid, non-viscous, ideal fluid, streamline flow, kinetic energy per unit mass, potential energy per unit mass and pressure energy per unit mass is always a constant. This has most application. On the basis of this, the questions are coming. Here some total of three energies, kinetic, potential and pressure energy is always a constant across any section of the pipe under flow. For any horizontal flow, we neglect this. If there is a horizontal flow, H does not changes, only relied on kinetic energy and pressure energy. Sum of these two remains a constant. Anyway, it is total, it is in accordance with law of conservation of energy valid. And sometimes in the NEET papers they are using a word of pressure head, velocity head, gravitational head or potential head. The meaning is, if you divide this by G, I can call this as velocity head, potential head or gravitational head, or it is a pressure head. Velocity head, sum of velocity head, potential head and pressure head are always a constant. Without G, there is just nothing but kinetic energy per mass, potential energy per mass and pressure energy per unit mass remains a constant. If they use the word head, it should be divided by G. Now coming to application of Bernoulli's principle. So even if LPS, how it operates is not important. You studied about the concept of carburetor or atomizer, or you are seeing the aeroplane wings made convex upward and concave down, all are based on the principle of Bernoulli. Not only this, whenever a train passes, we should not be very close to the train track. Bernoulli is coming in between. And even when we travel or drive the vehicles, maybe two-wheeler or four-wheeler, by the side if the heavy vehicle passes, again the Bernoulli comes in between. If you not taken care, then you have a chance of falling under the vehicle or the train. The reason is, when the train was passed, the air in between us V and the train is taken along with the train. The problem is here pressure falls and other side pressure is high. Air cannot come from the opposite side because vehicle is heavy, train or heavy vehicle. This side is easier because our vehicle or ourself is very lighter. What the system makes is the pressure is acting on us. To compensate this pressure, automatically will push towards the vehicle and we are having a chance of falling under the train or on the road. We may be so strong and so we are learned in the driving of vehicles, we fail because of Bernoulli problem. So we fall under the vehicles. Therefore, while overtaking the vehicle or we are driving the vehicle from the opposite directions also, we must keep minimum some distance between the two vehicles so that the Bernoulli's effect is minimum. So there is a small place, however, I can take over if you took the chance, and Bernoulli's problem may give trouble to us. Not only in case of train. There are some examples given, it may be carburetor or atomizer, the applications of similar way. So the questions on this law of continuity and second is on Bernoulli's principle. Now I am coming to the velocity of a flux and time of flow and rate and other things. Let us consider a liquid taken in a container to a height h. Liquid of density rho. There is an orifice. The liquid rushes out of this and falls to the ground at certain distance away from it. This is called as velocity of a flux, the speed with which the liquid comes out of through the orifice. The orifice seems to be at a depth h and it may be from the ground at a height h dash. Time taken to reach the ground may be called as t and this may be taken as a range. The questions are here the repeated. First, if you take velocity of a flux, velocity of a flux is root of 2gh. Here must be very cautious, h is not from the ground, it is from the top, free surface of the liquid to the orifice position. What the depth is considered as h, or if you want to know from the bottom, it must be 2g into h minus h dash. And as it just comes out, no velocity vertical, only it has horizontal velocity. You can calculate the time taken. Half gt square is equal to h dash. H dash is equal to half gt square. Therefore, the second relation can come to time taken to reach the ground. T is equal to, you know, h dash, the depth that has to reach is half gt square. If you t required, this becomes 2g upon h dash, 2h dash upon g with the square root. Time taken to reach the ground, where h dash is the height of the orifice from the bottom. Or I can come to the range, maximum distance where the liquid reaches the ground from the container. Range horizontal velocity is constant v throughout the journey. Time taken is this. You know that distance by time is velocity, and velocity into time gives you the range, v into t. V is nothing but 2gh, root of 2gh. Time taken is a root of 2h dash by g, which gives you root of 4h into h dash. For maximum range, it can be shown. Maximum range possible when h is equal to h by 2. Exactly at the center of the tank. If tank is completely filled, range will be maximum. For h equal to h by 2, it can be shown from this relation. These are the three. Very importantly, the questions are appearing. One is what is the velocity of a flux. Second, time taken to reach the ground. And third is the range Depending on the data given, you can switch over to the different relations.